Hello everyone, my name is Luke and welcome to this Pytorch tutorial series. In this video, we're looking at segmentation. So as per usual, all of the code you can find in my GitHub repo, link in the description. So in the previous video, we looked at detection. So we're on detection currently, and we looked at bounding box detection in the previous video. And we looked at what bounding box detection is and how we can make a simple model to do a single object bounding box detection. In this video, we're looking at segmentation as a different type of object detection. So we'll go over a few things similar to the previous video. A lot of the concepts in this video we've already seen before, so we'll make sure to only touch on the key concepts. So first we're going to look at what segmentation is, what semantic segmentation is as well, though we're not doing that too much in this one, seeing how we can use the UNet architecture, what the UNet architecture is, and why we need to use it for this segmentation. We'll also look at a different way of calculating the IOU. So we looked at the intersection of union in the previous video, and we'll see how we can do the same thing for a semantic segmentation or for segmentation. Okay, so firstly, what is segmentation? So as the name suggests, we are segmenting or cutting out the object from the image. So let's just rewind for a second, and let's say we've got a cat in our image, and I want to sort of detect where this cat is. We saw in the previous video how we could construct a bounding box around the cat or whatever object. But bounding boxes are a bit crude, right? So there's a lot of space in this box where there is no cat, right? So it doesn't really tell us too much information about the shape of the object. We can imagine such a case where, I don't know, whatever the object is, it's really sort of got an odd shape. And if I was just to put a crude bounding box over that object, we can see that the actual object doesn't really take up much of the space in the bounding box. So the bounding box just being a rectangle doesn't give us too much information about the shape. You can, right? There's no reason why you couldn't say that your bounding object is not a box. You could say it was a circle, right? You define some center and a radius. You know, it could even be a triangle, right? Whatever shape you like. And you might do that if your object, you know your object's going to take a specific shape to make sure that your bounding area is specific to what was sort of tightly on that object. What we do with segmentation is say that, well, we're not going to define some object or some shape and define some coordinates. We're going to generalize it even further to sort of any shape or any object. And the way we do that is by essentially classifying every pixel of the input image. So we've already seen image classification where we take an image like our cat here, and we give it a single label for the entire image. This one image has one label for cat, and that'll be some index of the output activations. What we're doing in segmentation is sort of every pixel of my input image. I've got some big pixels here. Every single pixel will get, a class activation. So I have some, I imagine that's some probabilities and some class activations from our softmax, defining some probability for each of the categories. The simplest case of that, which is what we're going to look at here, is background foreground segmentation. So there's only going to be two classes. So there are going to be two classes, right? And it's going to be, is this a background or is this foreground? So it's going to be, sorry, 1 or a 0, right? So foreground objects, we're going to say is class 1, and background objects class 0, right? And so every single input pixel in that 2D feature map or 2D input is going to have two outputs, right? So even if our input image is RGB, right, our output is going to be, right, this is by height by width. So 3 channels by height by width. Our output will be 2 by height by width. And we're going to use a cross entropy loss just like what we did with this sort of whole image classification, right? But with the whole image classification, the output of our model, we had one activation per class, we're gonna have one activation per class, but per pixel now. So that 1D output that we had for the whole image classification is now 2D, right? So it's not very different, right? We just treat each output sort of independently, and each one has some class activations. From this, what we should get is sort of a binary image where we have ones where our object is and zeros everywhere else. The benefit, one of the other benefits, other than, we get the exact shape of our object, is we can very easily expand this to multiple object segmentation. Right, so I said in the end of the previous video, if we wanted to expand the sort of single object bounding box to multiple objects, or n number of objects, so we have some unknown number of objects, then we have to do a bunch of complicated things to make that bounding box prediction generalized to larger numbers of objects. With segmentation, we really don't have to do anything else. Once we've got the labeled images, right, we could have as many sort of objects as we wanted in the image, and we'd use the exact same system, the exact same process. Now we would just have sort of a blob over here for one cat, blob over here for another cat. Furthermore, you could and you can use sort of traditional computer vision techniques to extract bounding boxes from these segmentation masks. So you'll get some segmentation mask. Let's just crudely draw what that might look like. We get some for one cat here, and we get another cat over here. And you could use something like blob detection and then contours. You could use OpenCV, and from this you can define the area of the blob and just use some bounding box to then once you've got the contours, you can then define a bounding box for those areas. So you can get bounding boxes from semantic segmentation, but the training procedure was a lot easier, right? So semantic segmentation is a sort of combination of this sort of classification and the sort of segmentation. So what we're doing in this tutorial is just going to be background foreground segmentation, but there's no reason why we can't have more classes in our softmax classification. So it doesn't just have to be foreground background. We can start to get finer and finer grain information. So maybe cats, dogs, birds, whatever. And what we'll get is we'll just sort of add more and more channels onto our output. But again, it's the same concept of classifying each pixel of the input image, right? So now you could have multiple objects within the same image, and we'll get different segmentation. We'll get a sort of segmentation mask for the entire image, but we'll also get the semantic, the meaning of what that object is. So again, you could do that with bounding box, but for bounding box prediction, you have to have an additional output that says, what is this object? In semantic segmentation, the sort of mask, this blob area, also tells you what the object is. And again, you can go further and get the bounding boxes from that. Okay, so that's just a very fast overview of what segmentation and semantic segmentation is. Okay. So it's commonly used in a wide range of applications, self-driving cars, medical imaging. It's very commonly used, especially since the introduction of the UNet. So the UNet is the architecture that we're going to use in order to perform this segmentation. So what is the UNet and what is so special about it? Well, we've already seen autoencoders and variational autoencoders, but we've already seen autoencoders, this idea that you could put an image in and we sort of downsample that to a smaller latent representation, and then we upsample back to the image size. And for something like segmentation, we need an image-to-image model. The input is an image, and the output has to be something that is the same size or similar size. Doesn't need to be exactly the same size as the input. So it needs to be a 2D output. So something like an autoencoder would work. The problem with an autoencoder is that we lose a lot of information, or potentially lose a lot of information, as we go down to a smaller and smaller latent representation, right? We've already seen how that is an issue in the previous videos. So you don't need to use an autoencoder. You might just think, well, why don't I just put a whole bunch of convolutions over my input image, but I don't downsample, so my feature map still stays the same size. I just put a bunch of convolutions. You can do a 3x3 kernel with one stride, one padding. That won't change the feature map or the image size. The issue with that is that it's going to take a long time before the receptive field of your outputs covers the entire image. What I mean by that is it's going to take a long time before each of your outputs, little pixels here, has enough information about the entire image to accurately predict whether or not it's foreground or background, right? If you didn't have a large enough receptive field, then a pixel from the ear of your cat up here, it's going to be very hard for the model to tell, does that actually belong to the cat, or is this just a gray pixel? How does the model actually know whether or not a particular pixel of the input belongs to the object or not? Well, it doesn't just depend on that specific pixel. It depends on all the pixels in the surrounding area, and potentially depends on all the pixels in the entire image, right? And because our convolutions only operate locally on the input image, it's going to take a lot of convolutional layers, especially if we have a large image. It can take a huge number of layers before sort of each output knows enough information to accurately predict what it is. So that's why you'd maybe use something like the autoencoder. We've already talked about how we have problems with autoencoders. So our UNet kind of mixes those two ideas together. It is essentially an autoencoder that's been rotated on its side, and we've got these additions of skip connections in our autoencoder. So let me just draw out what I'm talking about. So typically our autoencoder that we've seen before, maybe it looks like a bit like this. This is our encoder. We put our image in and we get our latent representation here. And then we decode out to try and get our image on the output. Essentially all UNet does is introduce some skip connections over the bottleneck. Right? If you were trying to learn a latent representation, or if you were doing some task where your input image is the same as your output image, this would not work. But we're doing segmentation where our output is the segmentation mask and our input is the image. So it's fine that we put this skip connection. We're not trying to compress the image. But because our encoder in our autoencoder is downsampling and compressing the image into a smaller latent representation, that downsampling, that sequential downsampling, shrinks our feature map into a smaller and smaller space, and also means that it's the receptive field of the latent variables in our bottleneck cover the entire image, right? So we can aggressively downsample the input image, and what that gives us is that means that each of the latent variables takes the entire image into consideration, but then we need to go back to the actual image size, and so we upsample with a decoder, but we lose information to latent representation, so we can add skip connections over that bottleneck. And if you sort of flip this on the side, sort of rotate this around that way, you get what is essentially our UNet architecture, encoder, decoder, and we have our skip connections going that way. So what these skip connections are, we'll see in a bit more detail. It's just the output activations of some layer here, and we concatenate those to the output activations of another layer, and then that goes into sort of the later layers. So that passes that high resolution spatial information, but the bottleneck here, because we've downsampled, we get the sort of high level overview of what's happening in the image. So we've got that fine spatial information as well as the large scale contextual information. Right, and that's our UNet here. Right. So before going to the architecture, let's just cover the changes that we do or have for the IOU. So this is called mask IOU, similar to before. This is just an nn.module class that will pass to our trainer to use as the evaluation method. As you can see, it's a lot simpler than our bounding box prediction. So I won't go over what we did for bounding box prediction, but hopefully you remember our IOU is our intersection over union, the intersection over union, which is equal to the area of, so my object, let's say that's our prediction, intersection with the area of my ground truth. So the overlap divided by the total area, or the union of A and B. So if I have my image here, and let's say this is my predicted segmentation mask, and this is the ground truth segmentation mask. The intersection is this area here, and the union is the sort of total area by both. And we saw how we do that with a bounding box in the previous video. Okay, now to get this for our segmentation masks is even easier. So what we're going to assume is the input into this is the binary, the binarized. So we've taken the argmax from our softmax prediction on the output, and we have a 1 or a 0, a 1 being it's the object, a 0 being it's not the object. And for our area of intersection, if that's a binary mask, then if I just take the area that is my prediction and multiply that 2D mask by the ground truth, all that's going to remain, all that's going to be non-zero, are going to be the areas where both of them are 1. So where both regions are 1, we're going to get this intersection area. You can see that in there. Everywhere else, 1 or the other is going to be 0, and so we'll get 0. Right, so what we do is we multiply that, we get a 2D feature map on the output. So these are 2D, these are both just 2D, here and here, and we multiply them together, and we can just take the sum. So we take the sum, we're essentially counting the number of pixels that both had a 1 in them, and that's our intersection area. And to get this, the sum or the union of areas, all we have to do is take the sum for our prediction, so count the number of 1s in our predicted bounding box, count the number of 1s in our target or our ground truth, and those are our 2 areas. Remember, to get the actual union, we need to subtract the area, intersection area, so we're not counting that area twice, and then we divide the intersection area by that union area. So hopefully that makes sense. Recap, multiply the 2 masks together, sum them up. That gives us the number of pixels, the intersection, the number of pixels that were both 1 in the same spot, in that same spot in that 2D grid. And then the union is just the number of 1s for one, the number of 1s for the other. Right, subtract that intersection area. Okay, and you can see naturally that if all of the pixels are 1s in the same location, then this intersection area here is going to be exactly the same as the union area. Okay, and that'll give us again a value between 0 and 1, 1 being a perfect prediction. Okay, so now let's have a look at how we actually construct our UNet. So let's scroll down to here. We can see our UNet model is constructed by stacking multiple of these UNet down and UNet up blocks. Each of these blocks is pretty simple. It's just a sequential block of sort of 2 conv layers. We've got a batch norm activation LU, conv batch norm LU max pool conv 2D. Each of our kernels or conv layers is just a 3x3 kernel, stride 1, padding 1, and we're doing the downsampling with a max pooling here. So each of these down blocks will just downsample by a factor of 2. Right. You could also put in some skip connections and make this residual, but I haven't done that here. I've just kept it simple. The up block does a very similar thing, except we've just replaced the max pool with a nearest neighbor upsampling by a factor of 2. So this will double the feature map size of the input. Now we've got input and output channels as well for both of those. So all we need to do is, for our encoder at least, is stack a bunch of these down blocks, right? And we'll eventually continually downsample our input. And that's what we've done here. I've defined one conv in layer, right, which is taking the number of channels in, going up to 64, but we're not downsampling the feature map. And then we apply we're going to apply 4 layers. So the input image size is going to be 128. So we downsample 4 times. That's going to give us an 8x8 feature map by the time we get to our last layer, our last block. Right. So pretty straightforward, just downsampling a bunch of times. Now, once we get to the decoder upsampling, it's very similar, but you'll notice that you can see we got this multiplied by 2 here. So for our down blocks in our sort of encoder, the inputs channels for one block is just the output channels of the previous one. That's the same for the first up block, but you can see that we've now got 2 times. 2 times, 2 times. That's because what we're going to do is we're going to take the outputs from this layer, and we're not just going to pass it to this layer here, we're also going to pass the outputs of this layer into the input of this layer here, right? And the output of this layer is going to go here, but we're also going to take the output of this layer here and pass it to the input of this layer here. And we'll get the output of that layer, pass it to the input of the next layer, but we're also going to take the output of the first down block and pass it to the input of the last down block. And those are our skip connections. So you can see we have some information that's going to go from the first down block all the way to the last down block, and then to the second down block, and then it's going to skip also to the second last, and then the third down block to the third last down block as well, right? So that's why we've got this 2x here. And then finally, we also are going to skip the output of conv in, concatenate with the output of the last up block, and concatenate together and pass that to the final conv out, which is going to be channels out, which will be 2 for our 2 channels, the 2 classes, foreground and background. So our forward pass implements that sort of unit structure. The first few lines there are very straightforward, what we were seeing previously with, say, the encoder for our autoencoder. And then it gets a bit tricky here. All we're doing is implementing those skip connections that I talked about. So the output of the final down block goes into the first up block, and the output of the first up block gets concatenated with the output of the third down block, concatenated together, concatenated on the channel dimension. So this is the dimension they concatenate over. So this is now not just 128, right? It's now 256 by height and width. You can see I've written the sort of feature map sizes, how that changed there. I think this is not quite right. Yeah, that should be 250 or 128. Anyway, and then we pass that to conv.5, and then we do the same thing, concatenate with down 2 output, and then so on and so forth until we get to our last concatenation, concatenating right up start the output of the first conv layer with the output of the very last up block, and then that gets passed to our final conv out layer. Okay, so all we're doing is we're just logging or keeping track of each of the outputs for each of the blocks and then concatenating them later on to the appropriate spot. Right, we have to make sure we concatenate them to a feature map that has the same spatial resolution. So here it's height divided by 2, width divided by 2. So we have to concatenate it with the output of down 1, which has the same spatial resolution. It doesn't need to have the same number of channels. You could change around the channels so the channels were different, but because we're concatenating on the channel dimension, all the other dimensions need to be the same. So hopefully that's pretty clear. It's not too complicated really, but as I've already discussed, it does help us out quite a lot. Okay, so let's start running some of these cells. So again, all we're doing here is passing that mask IOU that we just went through and implementing our model and passing that to our model trainer as well. And we're passing the dataset as well. Okay, so let me just skip to here. So let's have a look. We're using the Cub 200 dataset again. So I talked about in the previous video, but now we're using the segmentation masks. So I mentioned that this dataset has the bounding boxes, but it also has the segmentation masks. So these are just some binary masks, 0s and 1s, that just tell you the region of the input image that actually contains the bird. Okay. So the dataset I've already talked about in the previous video. The only difference here is that we've set this return masks flag to true. And all that's going to do is also pass we'll also get the mask data, right, which is stored in this segmentations directory. If you look at the dataset yourself, you can see, and the file name and everything is exactly the same as the image. We're just replacing the JPEG with a PNG, reading that with OpenCV image read, and we're just passing that to the transform as the mask. Everything else is exactly the same, and we just return the mask as well as the bounding box and the label. We don't really need those, but we'll return those anyway. So that's just what setting that flag return masks does. And we're doing all those transformations that we talked about as well with implementations that we saw as well. Okay, so is there anything else I need to talk about? No, I think that's about it for now. So we'll train this and we'll see how we go. It's gonna take a little while to train, but I'll get back when it's done. All right, so we've finished training finally. So we can see highest validation IOU was 0.78. Continuing to increase, very nice. Let's have a look at our model predictions now. So we'll pass some of the training, also testing images through our model. We get our output predictions. So here's some examples, and here's the ground truths. And let's pass that through, and so we can take that predicted output. Right, and we've taken the argmax over the channel dimension, so that'll give us our 0 or our 1. You can see, there we go, we've got our output prediction masks. You can see they're reasonably good, some better than others. One like this bird here behind all the sticks, it's struggled with a little bit. And some of the finer details in the legs. Legs kind of disappear with this one. Struggled with those, as you can see. But generally, more or less, not too bad. We can run a test to see what the IOU of the actual test, the unaugmented test data is. 0.82, so it's pretty good. You could train this for longer. You might want to scale up the actual model as well. Maybe make it a bit deeper, use some residual connections like I've talked about previously. But there we go. So it's pretty straightforward once you've got the model architecture down pat and you've got your IOU calculation, which we've already been over. Like I said, this is widely used in a number of applications. So medical imaging, if you want to identify tumors or breaks or something like that, you can use segmentation because those sorts of things tend to be, very oddly shaped, right? And you want to define precisely the region, so a bounding box won't cut it in those situations. You can expand it to semantic segmentation where you get a class, not just sort of foreground, background, like we've done here. You get a class and segment out different objects and classify them at the same time. So that's what I wanted to cover in this video. Hopefully you got something out of that. Thanks for watching. Remember to like and subscribe, and I'll see you in the next one.